Okay, this is part 2, Unit 9A. We're looking at functions and mathematical models. So again, these questions here, we did number 11 in the last video. We're just looking in each of the following situations. We're stating whether two variables are related in a way that might be described by a function. If so, which would be the independent and the dependent variables. So this one we're looking at, you're a bakery owner and you want to know how the demand for muffins, which is the number of muffins you sell, depends on the price you charge for them. So there's a couple of variables I see here. One is price, the other is demand. And the demand is definitely going to depend on the price that you set. Because if you set a price at a penny per muffin, then there's going to be high demand. You're going to sell out those things really fast, assuming they're good muffins, and so that demand's going to be really high. But then as you increase that price, that demand's probably going to drop down a little bit more. And then if that price gets really outrageous, like $10 per muffin, you're probably not going to have much demand. And so we would say that the independent variable here would be our price that you charge. But they definitely are related, the price at which you charge and the demand. So demand would be a function of price in this case. Okay, now we're going to be looking at some related quantities. We're just write short statements that express possible relationships between two variables. It gives us an example there of age and shoe size. So, for example, as a child ages, shoe sizes increase. But then note that, once a child is full grown, shoe size is going to remain constant. Recall, though, that the first variable listed is the independent and the second variable is the dependent variable. So in our first one, we're looking at the volume of a gas tank and the cost to fill. Okay, and in this case, we can say, as the volume increases, so the larger the gas tank, the cost to fill the tank will also increase. Because as you get a bigger and bigger tank, you're going to put more and more fuel in there, so that cost is going to increase. So the cost to fill the tank will depend upon the volume that you have in there. Okay, next we'll look at latitude and ocean temperatures on a given day. So latitude, moving north and south when you're looking at the Earth. So let's just look as the latitude increases. Okay, and if you think about that, you're getting further and further away from the equator. Okay, ocean temperatures. So ocean temperatures will decrease, or ocean temperatures decreases. Okay, because as you get closer and closer to the poles, which is getting farther and farther away from the equator, that means your latitude is increasing. Those ocean temperatures are going to get, in general, more cold, so the temperatures are going to be decreasing. Okay, another one. This takes us back to the good old days of riding the bikes. The rate of pedaling and the speed of your bicycle. Okay, if you think about it, as the rate of pedaling increases, in general, no matter what gear you're in, the speed of the bicycle also increases. Okay, you could also do rate of pedaling and pain in the legs. That was my most recent experience on the bike. As the rate of pedaling increased, the pain, the throbbing in the thighs definitely increased. But that would be the relationship that we see there in that function. So now we're going to talk about a couple of other brief things, and then we'll wrap up this section. So when we represent a function, there are three basic ways to represent your function. Okay, one way is a data table, and we looked at that with the temperatures in table 9.1. Okay, it provides detailed information but it can be really hard to manage when you get really big quantities of data. If you've got 10,000 data points, looking at a table with 10,000 data points can be really hard to take in when or to see all at once. So another one is you can draw a picture or a graph of the function. The graph is an easy way to interpret and consolidate a huge amount of information. You may not get down into as much detail as the table gives, but it really helps you get the broad picture. And then a third way is to write a compact mathematical representation of the function in the form of an equation. Sometimes people say a formula, like f of x equals 3x plus 2 or something like that, where that mathematical formula will model or represent whatever we're trying to model. So we're going to explore the use of graphs to represent functions. We're going to discuss that in 9b, but there's 3 basic ways. Now, just kind of a summary of using graphs just as a preparation for the next round. When you're looking at functions, you always want to first identify your independent and dependent variables. Then you want to identify your domain and your range, and that'll help you choose scales and labels on your axes. We're not going to look too deep into it this time. Again, this is just kind of a foreshadow of things to come. Although I will show you one graph here in a moment. And technology is a tremendous way to create graphs nowadays. Graphing by hand, not the most user-friendly, especially in the 21st century. And a lot of what you see will be graphs generated by technology. Okay, third, you make a graph using the given data points or the given data to plot points. And you may see a relationship, so if it's appropriate, you can draw a line or curve to connect those data points. So I'll give you an example of that here shortly. But that's taking all of that data and then plotting them on a graph. And then, before you make any predictions on this model, be sure to evaluate the data and the assumptions from which the model was built. Make sure you've got credible data before you put out your function. If you ever have a career where you've got to put out a function, say in economics, and you've got a demand curve, and before you want to throw out your demand curve, you want to make sure that the information that you had, your assumptions that you've made, is credible, or else that can get you into a lot of trouble. But those are kind of the 4 steps of creating a function. So we're going to just create a basic function here. So we're going to identify the independent and dependent variables. And usually, again, the independent variable is like the x-coordinate, so it's going to come first. But in this case, the speed is going to be our independent variable, and our dependent variable is going to be a stopping distance. Because if you think about it, the stopping distance of a car is going to depend on how fast you're going. And so those are going to be our independent and dependent variables. So independent and dependent variables. Let me just check my time here. Okay, we're doing good. Now next, describe the domain and range. So the domain always goes with our independent variable, and we're ranging from, the domain is going from 10 to 70 based off of this information. So 10 to 70 is our domain. So it's any speed between 10 and 70. The range, the lowest we go is 13, the highest we go is 312. So we're ranging between 13 and 312. Again, range always goes with dependent, domain always goes with independent variables. Okay, next one, make a clear graph of the function. Explain how you decide on the shape of the curve used to fill in the gaps between the data points. So I've used technology here, and got this put together. There's a lot of different things you can use, but again, in your class, you're probably going to be able to see this information and either be able to plot the points using technology, or given a graph, which one represents the situation that's given. But here we have our points. So the first thing I would do, again, if I was doing this on my own, is I would plot the points. So these would be the points that are given in this table right here. And then you notice that they are taking this general trend right here. And so we can, connect those dots, because it's fair to say that a car is going to be going between 10 and 20 miles an hour. You might be trying to measure the stopping speed at 40 miles an hour, but when you are doing your tests, the first test it might be going 39.5 miles per hour, the next one might be going 40.3 or something like that. So it's fair to connect those dots, because we're not going to be going exactly those speeds, but so making that connection there is fair. And then notice our way we've labeled our axes. We're going up by 10s here, because that's what we're going up on our table. And then going up by 50s, that would just be appropriate so that our graph, we don't have to draw a graph that goes to infinity and beyond here. Going up by 50s seems to be appropriate. And so the last thing is describe the function in words. So it looks like, as the speed increases, so as we increase our speed, it looks like our stopping distance is increasing. And one thing I want to point out here is, notice it's not a linear or straight line function. It doesn't go in a straight line like this. So it looks like, the faster we're going, it's actually adding more and more. Well, I guess if I were to draw the linear function between these first 2 points, we'd get something that looks like this. But that curve is actually increasing more and more. It's got a little bit of exponential taste to it. So just keep that in mind as you're driving. The faster you go, the longer or the more distance you're required. And it's not linear. So if you're going 20 miles an hour versus 40 miles an hour, it's not double the distance. It's more than double based off of this result here. So just be cautious of that if you're on the freeway or anything like that, to remember, with this given data. But that's how I would describe the data. It's not linear. It has a little bit more of an exponential feel to it. So as speed increases, the stopping distance is increasing at an ever increasing rate. So that wraps up 9A for us. If you have any questions, please do not hesitate to let me know.